So welcome everyone for this last SIPTA seminar before the end of your vacations. So we are very happy to have this last seminar to have Jasper the Bock, that most of you, or at least a lot of you know, to talk to us about robustness quantification. So without further ado, let's start this last seminar of 2025. And Gert, I leave you the floor.
Thank you, Seb. So I was asked to say a few words about Jasper, who's a long time ago, well, more than 11 years ago, was one of my PhD students, and I have to say that Jasper, for me, is one of the very clever ones, and he's one of the people I admire most. He defended his thesis, his PhD thesis, in May 2015, so about 11 years ago, and the thesis was on credal networks under epistemic irrelevance. And this was done a few years after he devised, in my view, an ingenious imprecise probabilities version of the Viterbi algorithm for imprecise hidden Markov models. And that with a computational efficiency that was at least comparable to that of the classical algorithm for precise hidden Markov models. And this, by the way, was one of the first algorithms to show that using imprecise probability methods to do inferences was not an entirely hopeless affair and could lead to a reasonable efficiency. And so in his PhD thesis, he significantly extended these ideas to more general Bayesian networks. Imprecise Bayesian networks, as we call them. So I think it's fair to say that his first efforts in imprecise probabilities were related to artificial intelligence and machine learning. But after that, he made important contributions to quite a number of other important advances in the field. So, well, he and I worked together on bringing imprecise randomness into the world. He also took the lead in linking choice functions to desirability and proving these representation theorems for choice functions in terms of those desirability models. And of course, he also advanced the field of continuous time Markov chains by leaps and bounds. Meanwhile, he supervised a good number of PhD students, and he is considered to be a very successful teacher. And you all know that he also served as a president of SIPTA for a number of consecutive terms. More recently, Jasper went back to his old love and started a new research line trying to bring imprecise probabilities to machine learning. And if I'm informed correctly, and I'm not always informed correctly, but if I'm informed correctly, then this is what he's going to talk about today. So Jasper, I'm really looking forward to what you're going to tell us now, and you have the floor.
Okay, thank you. That was a very kind introduction. Yes, indeed, I will be talking about some IP stuff related to machine learning. Great. So I'll be talking about robustness quantification. Now, before I get to that, I'd like to talk a little bit about where I'm from. I'm from the Foundations Lab for Imprecise Probabilities, which is led by Gert, who just introduced me. And there's a whole bunch of lovely people there working on all sorts of things related to imprecise probabilities. And they combine IP with different things depending on who you're looking at here. This might be a combination with quantum mechanics, with stochastic processes, or as far as this talk is concerned, is combining imprecise probabilities with machine learning. Specifically in that intersection, we are looking to robustness quantification. Now, before I explain what it is, I'd like to take a small step back and consider these two fields, because if you're watching this presentation, I figure you belong to at least one of these two communities. So to spice things up, to get your interest, I figured I'd start this talk with presenting two problems. One problem for every field. Problem one, machine learning is unreliable. I think this is nicely expressed by the following meme. So there's a machine learning model trying to classify things, and it thinks that this is a dog. Now in this case, this is pretty funny, but it isn't always funny. At some point, IBM developed a machine learning tool to recommend cancer treatments to patients based on their medical history. It started to make wrong recommendations there. at that point, if you don't tell the people that it might not be reliable, the prediction you're giving is no longer that fun. So that's the issue at hand. And to explain it a bit better, I'd like to set the scene. This also helps me nicely further on during this talk. So I'm not looking at machine learning in general. I'm looking at classification in particular. So you have this task, you're given some features. This might be the picture, this might be the medical data. And you've got this task of using that to predict the class. What can you see on the picture? What's the best treatment based on your medical data? And then the object that is used to do that is a classifier. It's a function, you put features in, it gives you predictions of the class as a result. And in this talk, I'll mainly be focusing on what is called a probabilistic classifier. That means that there's probabilities involved and you simply predict the class that maximizes, that has the maximal probability conditional on the features that you've been observing. And there's two kinds of these. Because you need these probabilities and you need to learn them somehow. And there's two approaches you might take. You've got the discriminative one, in which you simply try and learn these conditional probabilities, use them for the prediction. Or you can use a generative approach, in which you try to learn the actual joint distribution of the data, both features and class, and then condition that through Bayes' rule, and then use that to come up with a prediction. So for most of the talk, I'll be considering the generative case, but near the end, I'll also be talking a bit about the discriminative case. Okay, so that's the challenge, that's the task. Now, of course, we have these probabilities. We need to get these probabilities from somewhere. We need to learn them. And typically, you do that based on some training data. There's a bunch of data you have. You use it to learn in whatever way is your preferred method. Some probabilities, and then you've got other data, test data, for which you don't know or act as if you don't know the true labels, and you try and use your probabilities to predict the correct labels, and then you evaluate whether or not you've done a good job, yes or no. And typically, people also assume that both of these data sets have a common distribution underneath it from which they are, so to speak, sampled. They come from the same population, these two data sets. I will not always be assuming that. I will also be considering the case of distribution shift, where both data sets come from a different distribution, a different population. You might be learning your model based on data from one hospital, so to speak, and then you use it to recommend treatments for patients in a different hospital with a different demographic. Okay, so that's the setting. So what about this unreliability that I was talking about? Where does this come from? Why are things going wrong? Well, because there's a whole bunch of uncertainties that are playing a role. And it's already really at the heart of the basics of the problem. We are trying to make predictions for the true classes of test data, but that test data itself has a distribution underneath. And that means in particular that even if you know the features, then still for the very same features, some instances might have a certain class and some instances might have a different class. So it's already a gambling game from the very start. And that uncertainty that's inherent to the problem, I call that aleatoric uncertainty. It has to do with the fact that the data you plan on using the model for is already random. But there's a second problem on top, which is that you don't know what these probabilities are that underneath the test data. All you know is your probabilities right here, which is the probabilities you try to learn based on training data. Now, these may not be the same because all kinds of things can go wrong. If you have distribution shift, you have a problem from the very start. If you don't have enough data, then this training data is not necessarily representative for the training distribution. You make all kinds of assumptions to try and come up with your learned probabilities. For all these different reasons, there's going to be mistakes that you're making, and this uncertainty people often call epistemic uncertainty. Okay, so we have all these uncertainties, and these are the sources of unreliability in classification and more generally in machine learning. So that was problem one. So to keep things fair, I also have a problem for the IP community, which is that imprecise probabilities are arbitrary. What do I mean by that? So let's look again at this situation here where we're using probabilities to make predictions. In this case, we just have a precise probabilistic classifier, and we predict the class that has the highest probability given the features. So solve fine. Now, the problem is that often we have to admit to ourselves, look, these probabilities, this probability distribution, I don't really know exactly what these probabilities are. Enter imprecise probabilities. We use a credal set, which is our terminology for a set of probability distributions. Okay, so we play it safe. We don't say exactly that it's this probability distribution. We say, no, it's one of the distributions in this set. Now, in this case, we're still lucky because all the models inside this set, they all issue the very same prediction. They all issue predict class B. So our model is safer, but still we've got a unique prediction. So that's very nice. Of course, if the model would be more imprecise, this would no longer be the case. And if then all the models have different opinions, in this case, some of them say B, some of them say C. Okay, if we have that, then at that point we don't have a unique prediction anymore. We have a set-valued prediction, and now we're entering into the realm of credal classifiers based on credal sets on imprecise probabilities. A typical feature there is that sometimes they will issue more than one outcome because the different models in the IP set are disagreeing with one another. Now, this doesn't only depend on the model, it also depends on the features. Because if you have other features and you use the same model to make a prediction, maybe for those still they all agree and you still have a unique prediction going on. But of course, if you have more and more imprecision, I mean, at some point, basically all of the predictions become indeterminate. And that's also the problem. That's where I come from when I say that imprecise probabilities are arbitrary. Is okay, how much imprecision do we use here? How big is the credal set that we intend to use? If you know this, if you really have a good idea of how much you know about your probabilities, then that's fair. You just say, okay, this is what I know, this is my credal set, and you live with the consequences. But that's not always what we do in the IP community. Often we learn an imprecise model from data. And then, okay, what's nice, I think, if we learn it from data, is that we have this nice feature of imprecise learning methods that the imprecision initially is big. And as you get more and more data, the imprecision decreases and decreases and decreases. I think that's fairly natural. But on top of this, you still need to make a choice as to how quickly this imprecision will diminish. And this is something subjective. It's basically how safe do you want to be? How quickly do you want to learn from your data? This is something you really need to make a choice about. But it's an important choice because it will determine how much imprecision there is, and so to what extent your conclusions are determinate or not. And typically, okay, we just simply make some kind of choice there, and that makes the approach a bit arbitrary. It still works. It does a nice job at determining which kind of predictions we're not so sure about, which ones we're very sure about, but you have to make this arbitrary choice often as to how much imprecision to involve in the process. Okay, so that is problem 2. Then onto the topic of this talk, which is robustness quantification. This better at least solve these problems to some extent. I'll get to that later. First, what is it? What am I talking about when I say robustness quantification here? Back to the same setting I had before. I have a precise model. I use it to issue prediction. In this case, it's B. And I will continue to use this precise model. This is different from credal classification. I use the precise model to issue a single prediction, in this case, B. But alongside it, I also take into account what happens if I'm using a set of probabilities around that precise model. And in this case, this set of probabilities, they all agree with the precise prediction. And then I will say that this prediction is robust. So I have a precise classifier, it says B, but I add a label on top, I say this prediction is robust. Now this will depend on how much imprecision there is. If I add more imprecision, then I'm still using the precise classifier in the middle. It still says B, but I don't no longer call this prediction B robust because the imprecise model around it is disagreeing on which class I should do. And of course, if I add even more imprecision, then I'm definitely no longer robust. So what happens here, as I add more and more imprecision, initially I'm robust, but then at some point there's a boundary, and as if I have this amount of imprecision, then suddenly I'm no longer robust. And this is how we define robustness quantification. We try to quantify robustness in the following sense. We define robustness to be the size of the largest set for which my imprecise set, the set of probabilities, such that all the probabilities inside still agree with the precise prediction, for which my precise prediction is still robust. And this may differ from feature to feature. So if for a given set of features, I have a certain robustness, if I have a different set of features, I have a different prediction and a different level of robustness associated with that particular prediction. Okay, so that's very conceptually what robustness quantification does. How does it relate to these two problems that I've been talking about? Well, I think the IP problem is pretty evident. We're basically not suffering from it because we're not having to choose how much imprecision we want to have in our model. Instead, we turn this thing around and we're trying to find out how much imprecision there could be, we could allow without having a non-robust decision. So in that way, we're solving that issue. No need to set the imprecision. We're trying to find out how much imprecision there could be without changing our prediction. Okay, so that was problem 2. What's the relation then with problem 1, with machine learning being unreliable? Well, our aim is to use robustness quantification to try and tell for every given prediction to what extent it is reliable. Conceptually, the idea is if a prediction is robust, it means I can change the model a lot without the prediction changing. We think that's a meaningful indicator for that prediction being reliable. If you can do lots of things to the model, even if you made many mistakes, still you have the same prediction, seems like that is a reliable prediction. If it's very non-robust, if the robustness is low, it means that even if you perturb the model a little bit, you'll suddenly have a different prediction. So that provides a good reason to call that prediction unreliable, we think. Whether it works, of course, remains to be seen for later in the presentation, but conceptually, that's the connection with the problem I was presenting. Before I get to the results, I'd like to get you a bit of a more detailed view on how you do this. What do these credal sets look like? What do I mean by size? I don't want to get into too many details. I think a talk is not so suitable for that. I mean, you can look at the papers if you're interested in, but I do want to get you a bit more of a feeling for the way in which you might do this. And one important distinction, I think, is between local and global. Local, what I mean by that, this is really like we often do it in imprecise probabilities. So you've got a probability model and it's made up of different parameters. Like in this case, these black dots would represent the parameters of some probabilistic model. And then one way to perturb your model is to perturb all these individual parameters. So you make all these parameters imprecise. You've got a whole bunch of possibilities for each of the parameters. You take all possible combinations. There's a whole bunch of global models you get as a result. And that then is your imprecise model. This is typically what we do in IP. For example, if we do credal networks and things like that, or if we do credal and product networks, there's parameters in there. We make them imprecise. The model becomes imprecise. As the local approach, I'd like to oppose that against a global approach, which we don't use that often, but which I'll be exploring in this talk, which is to simply not care about all the details inside and just consider a set of probabilities around whatever this joint was that you started from, without really thinking about like what are the parameters inside this model, local versus global. Another distinction is, okay, what shape do these imprecise sets have? Many occasions, I think in IP, we're using epsilon contamination. It's a pretty clean method. So in that case, you start with a center distribution, the P that I'm using for my precise classifier here. And I'm doing a mixture with some other distribution, some arbitrary other distribution. I add epsilon percentage of an arbitrary other distribution. And I do that for all possible other distributions. And all these mixtures, they make up a set that contains the original center point that you started from. And this is a quite popular way in imprecise probabilities to come up with an imprecise model. But of course, you could do all sorts of other things. Distance-based IDs make lots of sense too. If you have some kind of way of defining a distance, and there's many ways of doing that, between two probability distributions, you can look at the set of all probabilities that are no more than the distance epsilon from the center that you're considering. So epsilon contamination or other ways of coming up with sets. And of course, both of these methods you can apply either on a local level or you can apply them on a global level. Okay, so with that, I hope you have a better view of how you might come up with these credal sets that are growing. As far as the size thing is concerned, like how do I define the size? That too should be clearer now, because in all these cases, what you have is you have a parameter. In this case, it's twice epsilon. And that parameter is controlling the size of the set of probabilities. The higher epsilon, the higher the set. So as for what is the size of a credal set? Well, we simply use this epsilon as a number that indicates how big the credal set is. Okay, so with that, I hope the general concept is clear, and then we can get to some results, see whether that works. And as far as results go, I think the first time this was tried was back in 2014. Well, that's the paper, so it was a bit earlier. And I was still a doctoral student then, and I went and visited Cassio de Campos and Alessandro Antonucci. I was working on credal networks back then. They also liked credal networks, so we sat together, discussed a bit, see whether we could come up with something. And we did. We came up with this notion of global sensitivity analysis for map inferencing graphical models. Now, you wouldn't recognize it by the title, but this was the first time we were doing robustness quantification. We didn't call it like that back then. I think we called it the global perturbation threshold. With hindsight, I think that was a mistake. Robustness is a rather better name for the concept. But nevertheless, I mean, the idea worked. We applied it then to Markov random fields and to Bayesian networks. And I don't want to get into the details of the results here, because I'd like to spend my time talking about some new stuff. One point is important, I think, which is that we discovered there that robustness correlates nicely with accuracy. So in this graph, if you're more to the right, it means you have low robustness. And if you're towards the bottom, it means you have lower accuracy. So to the right, you have predictions with low robustness, and you see that their accuracy for those predictions is also lower. And to the left, high robustness, you see that accuracy is high. And all these different lines are for different data sets. So across a whole bunch of different data sets, the lines clearly go down. So you have this nice correlation between robustness on the one hand and accuracy on the other hand. And that's very cool, because accuracy, you don't have access to it. You need the ground truth to evaluate accuracy. Robustness, on the other hand, you don't. Robustness, you can just compute using only the features. You don't need the true class to compute robustness. To have something that doesn't require ground truth, that correlates nicely with accuracy, is therefore something that we think is very useful. Now, this was for the naive Bayesian classifier, which is a very specific, simple case of the Bayesian networks. In that paper, we also did it for Markov random fields. This was an application related to facial recognition. It was a multi-label classification. So we were trying to predict a whole bunch of labels. We used the Markov random field to model the interaction between all these labels. And well, long story short, we observed something similar. Again, accuracy and robustness were correlated. Here, if you move to the right, it means worse predictions. And on the vertical axis, we've got robustness. So predictions that end up being more wrong. This year, the number is the number of labels that we are misclassifying. If you are misclassifying more labels wrongly, then robustness goes down. So again, we've got this nice correlation going on. And then a couple of years later, Cassio and a whole bunch of different co-authors, Dennis Mawa, Fabio Cosma, I think are two people that are fairly well known in the IP community. If I'm not mistaken, they're also here in the audience, and a whole bunch of other co-authors have written a whole bunch of papers, again exploring this very same concept, but now instead of for Markov random fields and Bayesian networks, they did it for some product networks, and they did it for generative forests. And they have a whole bunch of experiments. I don't have time to discuss them all, but I think the main conclusion there is that, again, they found that once more, robustness correlates very nicely with accuracy. This is for a whole bunch of different data sets. On the left is for some product networks. On the right is for generative forests. And you see that as robustness increases, the accuracy also goes up. Okay, so the main conclusions from takeaway message, robustness correlates nicely with accuracy. And two, you can do this thing for different types of model architectures using basically variations on credal classification kind of architectures to compute these robustness measures. Okay. And then recently, we started thinking about this again. And that's myself and Adrian de Tavernier and Rodrigo Lassans, we started thinking about this concept again. And the reason why is because we started thinking about it from let's say, a different angle. We were looking at these kind of things. So remember, classification can be unreliable because you have all these uncertainties. Now, okay, what to do if you have these uncertainties? Maybe you're unreliable. So one thing you can do is you can try and find out, put a number to how unreliable your prediction is. You issue a prediction and you accompany it with a number saying it's very unreliable, or I think it's very reliable, and so on and so forth. And if you have this kind of setting here, a very natural thing to try and do is to quantify all these types of uncertainty here, to try and put numbers to how much uncertainty of potentially of different kinds there is. And this is a whole field. I have the impression it's booming. I will not talk too much about it because Eike Hullemeyer gave a very nice SIPTA seminar a couple of months ago about this very topic. So I will not be repeating all the ways in which you could try and do that. But we think that robustness quantification fits nicely into this picture, because there's an inherent problem with uncertainty quantification, I think, and that is, okay, you can never aim to quantify uncertainty in all settings. The only thing you have to try and quantify uncertainty is your training data. So you're using this training data to somehow try and quantify to what extent you've got aleatoric and epistemic uncertainty. But you've got all this stuff hidden underneath that you have no access to whatsoever. If you only have limited data, then okay, this training data may not be representative for the underlying distribution of your training data. And if you have distribution shift, well, then these are different anyway. And how on earth would you ever discover that unless you've got access to test data? If you only have the training data available, there's a whole region here which you have no access to. And so if there's lots of distribution shift, or there's limited data, there's a boundary to the extent to which you can try and quantify uncertainty, I think, conceptually. And robustness, how does that fit in this picture? Well, it takes a completely different stance. It just gives up on trying to quantify epistemic uncertainty and aleatoric uncertainty. It says, let's not try and do that. Instead, what are we doing? We're trying to find out, okay, there's going to be a difference here between p-test and p-classifier. There's going to be some epistemic uncertainty, but we don't know how much. It's difficult to find out how much. So instead, we flip this picture around and we try and find out, okay, how big a difference can we allow for? Maybe there's lots of epistemic uncertainty, but if it doesn't matter, if the decision doesn't change, even if I change the model a lot, then who cares? And that's exactly what robustness quantification does. It tries to find out basically how much uncertainty there can be, how different the real distribution for the test data can be from your learned distribution without there being a difference in the two predictions. Okay, I think this slide really summarizes it nicely. So you got some epistemic uncertainty there. In uncertainty quantification, you will try and find out how different these two are. Robustness quantification will try and find out how different they can be without changing the prediction. So it's really a major conceptual difference between robustness quantification and uncertainty quantification. Okay, so that's one thing, our point of view differs. Now let me remind you of these distinctions. You've got local and global, and we had absolute contamination and then other ways of coming up with credal sets. So far, all the things I've talked about, the things that have been done in the past, they are local, and almost without exception, they all use absolute contamination, because these are the things that typically people are used to doing in credal classification. Now I'd like to open up this global part here, and I'd like to combine global with epsilon contamination. And this ends up being very simple. So if you just epsilon contaminate the joint model and you define robustness the way we've done it, then the robustness is simply given by this super easy formula on top. It's just this fraction with the delta inside, and the delta is simply the difference between the probability of the features and the predicted class minus the probability of the features and the second most probable class. So that's it. So it's a very clean, simple formula. Maybe it's a bit too simplistic, remains to be seen, but you can do this global robustness very easily. It takes a lot less work than trying to do this local stuff where you have to come up with all kinds of clever algorithms to compute robustness. Okay, so now we've got these two at our disposal, global, or we can use existing algorithms for the local one. Okay, so we can do this at least conceptually for global perturbations. Now onto some results here. So there's a lot to be seen here in this graph, lots of things to explain. Let me start on the top. So there's a whole bunch of different metrics that I'm using. The first 5 are those are all uncertainty metrics. So I don't wish to go into too much detail about which they are all, because they serve as a point of reference here. But okay, just very briefly, UM, that's the probability of misclassifying, not according to the real distribution, but according to the probability that you have learned. So 1 minus the probability of your predicted class according to your trained model. UH is simply the entropy of the trained probability distribution, conditional on the features. And then the next 3 are aleatoric, epistemic, and total uncertainty, defined using ensemble techniques. So it's this kind of information theoretic kind of standard decomposition that people are nowadays often using to define, try and define aleatoric, epistemic, and total uncertainty. So well, the total is the entropy of the average of the probabilities in ensemble. The aleatoric is the average of the entropies, and then the epistemic is the difference between the two. Okay, so there's a whole bunch of methods which are being used to quantify uncertainty. And then next to that, we've got local and global robustness quantification that we are putting against that. Okay, so that's what the colors mean. Then what can you see on these graphs here? Let maybe look at the middle graph. So what are we doing here? If you look on the right here, everything coincides. Here we're using the whole test set, and on the whole test set, we're just looking at the accuracy, and it's the accuracy of the model. The model stays the same. It's the metrics that are changing. So this is just the accuracy of the model there. What happens here then is as I move to the left, what I do, this is all the test data, and now as I move to the left, I remove data. I remove the data that I think is the most difficult to classify. Depending on the metric, this would be data with the lowest robustness that I start throwing out, or this would be data with the highest uncertainty that I start throwing out. And so I allow myself to remove the most difficult instances, look at the accuracy on the remaining ones. And if I do that, if I do a good job, then as I move to the left, these graphs should go up. Okay, so higher is better in that regard. And the nice thing is that robustness, which is yellow and green here, local and global, end up performing better than all these uncertainty metrics that we are considering. So that's already very nice, I think. What else can you see? We have 9 pictures here. From top to bottom, we're playing with the size of the training set. So here we have a training set of 100 data points. And then as we go lower and lower, we go to very small training sets. In this case, even just 25 training data points. And so what we see is as the number of training data decreases, we see that the separation between all these methods become more clear, and we see that the performance of robustness is typically way better than those of uncertainty metrics. In fact, the performance of the robustness stays pretty much the same unless we really go towards very extremes. And then something else, if you move from left to right, this parameter gamma here, gamma is the amount of distribution shift. So the extent to which the distribution of the training and test data is different, which we were controlling here. And you see if there's more distribution shift, then there's a much bigger difference between the different approaches. And again, we seem to be able to cope very well with distribution shift, especially if you combine it with having very small training sets. Now, in this graph, an important thing to mention is that all of this is artificial data. So we picked two distributions, one for the training data, one for the test data. We sampled data ourselves so as to be able to really control distribution shift and study the effect. Well, of course, you don't necessarily want to do this on artificial data. I'll get to real data later. One extra point, which I think is quite nice. So conclusion from this all, we are competitive with uncertainty quantification, and we can deal very nicely, I think, with distribution shift and with small data sets. Now, this is the second set of graphs. So this here was the performance accuracy-wise. Now, all these graphs are averages over several runs, so to have a kind of a fair overview of the performance. Now, these are the averages. These are the standard deviations. And this is pretty nice, I think. So what we see is not only are we performing better on average, but we do so much more stably so too. The green and the yellow are systematically at the bottom here. So there's much less variation in the performance of how well we're able to kind of order data points from easy to difficult. Okay, so another check mark for robustness quantification. Next up, is this just because we were using artificial data? It's not. This here is some results for real data. This graph is very similar to these graphs here, but we flipped the graphs. So now at the left side here, right here, this is if you just use all the test data, and then from left to right, we are removing the most difficult ones. Difficult according to whatever metric you are using. This is called an accuracy rejection curves, and those are the ones I'll be focusing on for the remainder of the talk. And so as you as you throw away more and more of the difficult ones, it should go up, and clearly we see that again it does. And here we start to see a difference between the local approach and the global one. The local approach is winning here, whereas the global is a bit in the middle in the bunch. Okay, so, and if we look at the standard deviation, then similarly we see that both the local and the global one perform more stably than uncertainty quantification. Okay, so we continue to be competitive and be more stable, but we're starting to see difference here between local and the global approach. Now, what else? For artificial data, we looked at the size of the training set. In this example that I showed you for one particular data set here, the training set was of size 200. Now, we also studied the effect of the size of that training set. You see this on this graph. So here, the 200 you see on the bottom. So there, I'm summarizing the performance of this graph. And I'm summarizing by the area under the curve. So I'm looking at the area under these curves, and that I use as a number for how good that particular approach is able to order things from easy to difficult. Okay, so here for 200, you see that, okay, the local robustness metric is doing a good job. And you see that actually the global one is not doing such a good job. And if you look at the effect of the size of the training set here, you see that, okay, the local is especially for low, small sizes of training sets is really doing a very good job. The global one here is not doing such a good job. And as you add more and more training data, if it becomes very big, you see that it's crossing here. So for large data sets in this case, it seems that uncertainty quantification becomes better than robustness quantification for the local version also. Okay, now this is for one particular data set. We've done this for a whole bunch of different data sets. Like this is another example. In this case, still the local is doing a very good job. The global is doing a very bad job. And all the uncertainty quantification stuff is somewhere in the middle. But now, even near the end, it's not so that uncertainty quantification is taking over. This is yet another data set, and here, but strangely so, suddenly the global approach is also doing a very good job. So here, both types of robustness quantification are working very well and are outperforming uncertainty quantification. We're not sure what the reason is, but we think it has to do with the fact that for this data set, as you gather more and more data, eventually the accuracy goes to 100%. So you're just pretty sure of what to do. So there's no aleatoric uncertainty here. So it's typically only epistemic uncertainty. And so one might argue that you can infer from this graph that if there's that we're typically good at quantifying, not quantifying the epistemic uncertainty, but at least seeing what the reliability consequences are of there being uncertainty of an epistemic nature. Okay, so also for real data, we're competitive, we're good with small data sets. Now, I've been playing this competition here between uncertainty quantification and robustness quantification. I don't really intend to have a competition here because my next point I'd like to argue is that they can be very compatible. So what you're looking at here is a whole bunch of test data. Every point is a test data point. The red ones were misclassified, the green ones were correctly classified. And on the axis, we've got on the bottom robustness, and on the vertical line, we've got one of the uncertainty metrics. And so left means low robustness, right means high robustness. On the bottom means lots of uncertainty, on top means almost no uncertainty. Okay, so you should be bad if you're in the lower left corner, because you're not robust and you have very high uncertainty. And in the seed, if you look at the data points, you see this, you have this tendency. And you also see, I think if you look at this picture, that there's a benefit to using both things. For example, if you would use only uncertainty to order these, then you would go from bottom to top. You'd say, okay, you're going from difficult to classify to easier, 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 easier. That's what you would then predict. But then if you look at this point, for example, it has very high uncertainty. But okay, it's not a problem because it also has very high robustness. So this uncertainty basically is not a problem there. And you see that indeed it's also correctly classified. So next up, we started thinking about how can we combine these conceptually very different things. And this graph convinces that maybe this is worth a try. So we see on the graph that they might be complementary. So we try to combine them. For now, with a very simple approach. So what we did, we just ordered them according to uncertainty. That means from bottom to top. And then we ordered them according to robustness, which means from the left to the right. And then we basically merged these orderings. So if you've got very high uncertainty and low robustness, you'll be way up front in our new ordering and vice versa. So we're kind of merging these two orderings, and the weight we give to the two to uncertainty and robustness, this one we do simple, just a convex mixture between the orderings with using a parameter gamma that determines the weight. And we learn that parameter on the training data. So on the training data, we go and learn to what extent do we want to take into account uncertainty, to what extent do we want to take into account robustness. And although the approach is simple, it already worked nicely. These are the results. So these are, again, these accuracy rejection curves. Higher is better. If you, the blue here is robustness quantification. The yellow is uncertainty. I mean, none of them is really winning. Sometimes the one is better, sometimes the other is better. But the hybrid approach is on top of both. So by combining forces, using them both, we can outperform, so it seems, the two approaches separately. Now, this is just for one data set. We did this for a whole bunch of data sets. So the numbers you're looking at here are, again, the areas under the curve. So in these graphs here, the numbers in the table are just the area under whatever the line is that you're looking at. So here, for example, we are looking at uncertainty quantification. That's the area. This is robustness. Blue is robustness, the local one in this case, and then our hybrid approach, which is for this data set winning. And we did this for a whole bunch of data set, combining uncertainty with the local one and combining uncertainty with the global one. Both are different hybrid methods. We see that we're winning a lot. Overall, these data sets, hybrid is often the best approach. And if it's not, then often it's robustness that is winning. There's only two cases, at least if we combine with the local one. Here, uncertainty is winning, and here, uncertainty is winning. And as a byproduct of this approach, I think this is also rather nice. We've got this gamma here, which is determining to what extent you use uncertainty and to what extent you use robustness. So here one means, okay, we just go for uncertainty. Uncertainty is the thing we use, only that. Whereas if you have very low gamma, it means you are going to take into account robustness more. And there's still many improvements, I think, to be made here. For example, here, if you look here, for this data set, it says here that we're taking into account mostly uncertainty, but in fact, that's not so wise a decision. We should have used more robustness, because robustness is doing a much better job. So this is due to the fact that we are learning gamma on the training data. So there's some overfitting going on there, I think, which we still need to solve. But even with our simplistic approach, I think we've demonstrated that it can pay to try and combine uncertainty and robustness with each other. Okay, so we're not only competitive, but we're also complementary to uncertainty quantification. Good. Now, let me take you back again to this distinction between local and global and epsilon contamination and other stuff. So I already combined global with epsilon contamination. Next up, I'd like to move to this other stuff, to use more a distance-based approach. We looked at several types of distances, especially this was because we wanted to apply the methodology to continuous features. And epsilon contamination for continuous features, well, you can do it, but it doesn't work really well in the context of robustness classification, at least not if you're directly contaminating probabilities. If you're contaminating parameters somewhere in the model, that works, but if you try and contaminate the probabilities, and you do it with epsilon contamination, then robustness is not working. Basically, nothing will be robust. This is basically due to the way these things are defined. Technicalities, don't want to get into it. But so what we did, we came up with this, we started looking at this distance metric, which is basically bounding multiplicatively how different two distributions can be. So this ratio between probabilities is being bounded by this distance. So the maximum ratio, either P1 on top, either P1 on the bottom, it doesn't matter, you're bounding that. That's a distance. And in this way, multiplicatively, you're kind of building a credal set around the center of point. So we looked at this other approach using that particular metric. And we combined that, we used that, and we did it in a global way. And then it was pretty simple. Again, we found just clean formulas for the robustness. If there's some discrete features, this is the formula. If there's only discrete features, I'm sorry, then you have this formula. I don't want to really get into it. I want to focus on the case where we have at least one continuous feature because it simplifies then the formula. It's simply this. It's super simple. It's just the square root of, on top here, the probability of the features and the predicted class. And on the bottom, we've got the probability of the predictions and the second most probable class. Okay, so conceptually, at least, you can define this using different things than epsilon contamination, and we did it here for the global case. And so what's nice about this, I'd like to remind you of this distinction that I was making between generative on the one hand and a discriminative on the other hand. So generative is you learn the joint distribution. Discriminative, you're only learning the conditional distribution. And so what is nice about this particular formula is that you can rewrite it as such. You can change these joint probabilities into conditional probabilities because we're conditioning on the very same thing. So by base rule, it's just we're dividing by the same thing. So it just falls out and we get a similar formula, but now with conditional probabilities. The nice thing about this is that we don't need the joint. We only need the discriminative part of the model to evaluate this specific robustness metric here. And there are two sides to this coin. Like on the one hand, this may tell you that, okay, this particular distance that we've used, maybe it's about simple because we're only using like part of the information. On the other hand, what's very nice about it is that, well, you only have to know that part of the information. So now you can start using this method for classification methods that are discriminative. Okay, and so we tried this. We use it for a random forest, and this is the result. So we only have the global one because for this distance metric, we don't have an algorithm yet for local robustness quantification. So when you only have the global one, and we're comparing it to a bunch of uncertainty metrics. And in this result, we see that, well, we're doing a good job and it's fairly comparable, but we're slightly better than simply using the predicted probability of misclassifying. Okay, this is for a training set of 5,000 data points. We also looked what happened if you have a much smaller training set, 300 in this case. Results are similar, but the distinction becomes clearer between uncertainty on the one hand and robustness, this global robustness metric on the other hand. Now, truth be told, this is for a random forest. This is for one particular data set. We also tried this for other data sets, for other types of classification method, logistic regression, gradient boost, all sorts of things we've been trying out. And to be fair, it's not always looking as good as it is here. So it really depends on which kind of model you're using and which kind of data set that you are considering. And yeah, we're not sure yet. We don't understand fully yet for which types of data sets robustness is typically more important and for which ones it's uncertainty that's more important, or why for different types of model architectures, on the one hand, the one is performing better, on the other hand, the other is performing better. We are in the midst of exploring, basically understanding what's going on underneath there. We also are not sure yet whether this is due to the fact that this is discriminative in the sense that we're using this rather simple formula, and that comes into play. We don't know what would happen if we would use a local approach, whether we can make a local approach discriminative. All of that remains to be seen. But we think it's nice that at least it's possible to apply this methodology in a discriminative setting, and that at least in some cases is working nicely. Okay, so also in this discriminative setting, we've got a whole bunch of points going for us, I think. And I think it's pretty clear, right? There's a whole bunch of check marks here. This is all fairly preliminary. Sometimes we've only done it for very simple models. Sometimes we've only explored some aspects of that. It remains to be seen to which extent these points will remain true if we explore more complicated architectures. We don't know yet, but we think at least the fact that it's working already, we find it exciting, and we hope that you like it too, and that maybe you can contribute to moving this idea forward. Now, there's a little bit more. There's some things I decided to not talk about, just to focus the presentation. In case you're interested, I just give you kind of an overview of what there is. So one thing, another distinction you could make is direct versus indirect. In IP, we're not always just kind of perturbing probabilities. We are often also perturbing like the things underneath the learning process. So we often do things like using sets of priors, and then as a result, we've got imprecise models. So this would correspond to, for example, using the imprecise Dirichlet model. That would be a case. So this you can also do, and you can expand imprecision in this way, and it behaves a bit differently. But we still don't understand like what the nuances are of the difference between these approaches. So hence, I didn't really go into that. Something else here. These are some results from the very first paper, where we were splitting the predictions according to some other criterion, in this case, the emotions of the people. And we observed that robustness can vary quite different, can vary heavily depending on kind of which category you're looking at. So this could be useful in kind of a fairness setting, where you distinguish between male and female, and you find out whether for one of the categories, maybe predictions are more robust or less robust. And then finally, and I think this is very nice, you can use robustness quantification for model selection. Because what's important, robustness is a feature, is an aspect of the features itself. So for everything you're trying to classify, you've got a prediction and you've got robustness. So in model selection, typically you've got a data set and people try and find out, okay, which model will I use? Robustness allows you to decide for each particular test data point, for data point per data point, which model way I use for this particular data point. For example, the one that's most robust. And this has been tried on a couple of occasions. I think it's a nice application of this idea of robustness. So these are the things we have been doing as far as what we perhaps like to try. An important issue, I think, is calibration. This number, the size of the credal set, the robustness itself, depending on the model architecture, this has kind of different meaning. So comparing between model architectures is difficult. We solve that for now by just looking at how it's capable of ordering from easy to difficult, rather than using the actual number, just the order. But if we want to go beyond that, we'll need to calibrate some way. So this we'd like to think about. This was all for classification. You can also think about doing this for regression. Now it's very different because in classification, it's in discrete steps. You have a unique prediction and then two. In regression, this doesn't happen. It's all continuous movement there. So conceptually, you have to change it, but still, we think it's possible to do this for regression. And then finally, we think it would also be useful to combine, to look at this in the setting of conformal prediction. And all that I've been talking about now, it was really robustness to basically to epistemic uncertainty. We think that in the context of conformal prediction, we could study robustness against aleatoric uncertainty. But well, all of that is future work. I'm just throwing that out there in case you find it interesting. But for this talk, that will be it. I hope you enjoyed it. I hope you like robustness quantification, or at least understand it to some extent now. And I'd be happy to take questions.